All right, Earth Science class. This is the second lecture from Chapter 3. We'll be covering sedimentary rocks in this lecture. So sedimentary rocks are important because they cover approximately 75% of all land on Earth and virtually the entire ocean basin. Now, even though that's true, it only comprises about 5% of the Earth by volume of the outer 10 miles. So it really is the icing on the cake. And the reason why, it's one of the reasons why sedimentary rocks are important is because they contain evidence of past environments and also evidence of past life. They also contain important economic resources, coal, oil, other fossil fuels, natural gas, uranium, iron, aluminum, magnesium, phosphate, and even groundwater resources. So sedimentary rocks are the products of weathering, of mechanical and chemical weathering. When rocks are exposed at the Earth's surface, they undergo that weathering process, and that weathering process produces sediments. It also produces soluble constituents, which are carried in water, and that material is transported downslope by gravity to low-lying areas. We call that mass wasting. Sediments are then deposited in these low-lying areas and subsequently buried by more and more sediment. And as this deposition continues, those sediments can lithify and become a sedimentary rock. And so there's three types of sedimentary rocks. There are detrital sedimentary rocks, chemical, and organic sedimentary rocks. So here's an example of different environments where sediments can be created, transported, and then deposited. Here we have mountains, exposed metamorphic igneous or even sedimentary rocks, weathering away, being carried downslope by either wind or water to a depositional setting like a lake. Okay, sediments can accumulate in lakes. Rivers carry a lot of sediment and they can deposit a lot of sediment, so they'll leave behind deposits on riverbanks and also on deltas. Okay, glaciers are slow-moving ice rivers, and they carve out landscapes, and they'll deposit a lot of sediment at the end of a glacier right over here. Okay, in really dry areas, wind plays a big factor in picking up smaller size sediment, and they can deposit dunes in deserts. And ultimately, the wind and also river running water will carry a lot of sediment out to the ocean. And the ocean is really the resting place of most sediment. This is the lowest lying areas of Earth, and they accumulate a lot of sediment. And this is where sedimentary rocks will form over time as more and more sediment deposits. There are other situations where organisms will create colonies in low-lying tropical waters, reefs, and that would also create a sedimentary rock called limestone. So let's talk about detrital sedimentary rocks first. These are sedimentary rocks that form from sediments that have been weathered and transported. They're mainly made up of broken down pieces of other rocks, clay minerals. So usual suspects are quartz, feldspars, and micas. And the way you distinguish between the different detrital sedimentary rocks is based on particle size. That also clues you in on the environment of deposition, the particle size. And so the common detrital sedimentary rocks include shale, sandstone, which is this pictured right here, conglomerate, which is this guy right here, and breccia. Okay, so this is how you categorize detrital sedimentary rock. It's based on particle size. These guys right here are the largest or the detrital sedimentary rocks with the largest particle size. They have particles that are greater than 2 to 4 millimeters in diameter. Okay, so that includes granules, pebbles, cobbles, and boulders. We have a conglomerate, okay, and we have a breccia. The difference between the two is the shape of the clasts that make up the rock. Essentially, a conglomerate looks like a lot of other rocks kind of glued together, and rounded rocks especially. Breccias are different because their clasts are angular. You see that here. they're angled like that. Okay, if you go down in terms of particle size to about 1/16 to 2 millimeters in size, that's essentially sand. And creatively, geologists call this type of detrital sedimentary rock sandstone. Okay, there it is right there. It's pictured right there. What it feels like the rough side of a nail file or grip tape from a skateboard. It's just a rock that's made up of sand kind of all compacted together. And then if we go down in particle size to a smaller particle where we have silt or clay, the smallest particles, you can have siltstone, okay, or shale. Shale will be made up of clay, okay, and siltstone will feel kind of gritty, and shale feels really smooth because they're made of really small particles. Okay, shale is made up of those really fine-grained particles, and they form specifically in quiet, non-turbulent environments where you have gradual settling of very fine sediment. Think of mudflats, lakes, floodplains, or the deep ocean basin. That's where you'll see the gradual settling of really small sediment. Okay, you can see some pictured here. They have facility, so that means that you can kind of split them open. They have weaknesses along these planes here. And those thin layers are called laminae. It crumbles easily, and it forms gentle slopes as a result when you see outcrops of it, like in canyons or ravines. And it's the most abundant sedimentary rock. Okay, you can often find fossils of plant organisms within them, imprints of these, and that's it's a little rarer to find plant fossils because a lot of times they might not have hard vascular parts that can be preserved easily, so shales provide a unique opportunity for this. And then here's an example. This is at the Grand Canyon. We have a lot of exposed rocks here, and just by looking at it, you can tell where the shales reside because of the gentle slope that you see here. This is where you'd find shale because it crumbles very easily, so it often forms these gradual slopes. These steeper slopes are typically harder rocks, so these would be your sandstones or limestones. So speaking of sandstones, that's a detrital sedimentary rock made up of sand-sized particles. They form in a variety of environments. They can form as river deposits. They can form in deserts or dunes from deserts. And they can form in beach environments or shallow marine environments. This is the second most abundant sedimentary rock. Quartz is the mineral that's most abundant in sandstone. Okay, quartz is very weather resistant. It sticks around for a long time. That's why a lot of the beaches that we have here in Florida have a lot of quartz sand in them because they get reworked by the ocean and they stick around for a long time. Now there are many different types of sandstone we won't get into exactly. It's just different amounts of different minerals. For example, if it has more feldspar in it, we give it a different name. Here's a close-up view of a quartz sandstone. So if you look at it closely, you can see the individual grains of quartz sand kind of all just glued together, essentially. And then these are the environments where we find them. This is the modern environment where it would form, or one of the environments. This is the Colorado Great Sand Dunes National Park, where we see these beautiful white sand dunes form and move with the shifting winds. That can be preserved in sedimentary rocks. This is Zion National Park in Utah. You can see the Navajo sandstone. This is in some places over 2,000 feet thick of just sandstone. And they show a typical structure of shifting sand dunes. So this is what the environment was like in the past. That's why sedimentary rocks are important, because this is the environment in which they form. Okay, so if you see a sandstone like this and you know its age, so this occurred in the Jurassic, then that means this portion of Utah in the Jurassic was a lot like the Saharan Desert or the sand dunes in Colorado. Okay, the last detrital sedimentary rock that have the largest class are conglomerates and breccias. Conglomerates, they consist of rounded gravel-sized or larger sediments, and breccias are kind of angular, okay? Both are very poorly sorted. What that means is that they have class of different sizes. So you have big ones and then kind of smaller ones that are intermixed all over the place. And this is a kind of typical conglomerate deposit here. So here's a picture. This here is a conglomerate. Notice that they have rounded clasts. That means it's been worked by water, perhaps for thousands of years. So it's a little further away from its source being the areas where this material eroded, maybe from a mountainside. And then this is a breccia. And if you look here, you can definitely see the angled class in a breccia. Okay. And this indicates that these were deposited much closer to the source, meaning like perhaps it was a landslide close to a mountain, or a lot of material just kind of mass wasted and fell downhill and deposited, and there wasn't enough time or water to round the edges of these clasts. One notable discovery, speaking of a detrital sedimentary rock, was I think in 2004 the Mars rover took a picture of a conglomerate on Mars, and that was a huge discovery because what that indicated was that at some point in Mars's past, they had flowing liquid on the surface of Mars, and long enough, for thousands of years, to be able to round the clast to create a conglomerate. Okay, so presumably it's water, most likely saline water, like ocean water, essentially. Okay, the next category of sedimentary rocks are chemical sedimentary rocks. These form from precipitated material that was once in solution, typically water. So precipitation occurs in two processes, organically or inorganically. Inorganic essentially just means evaporation or some sort of chemical activity. An organic process involves organisms. Typically water-dwelling organisms will remove dissolved solids from the water to create their shells, exoskeletons or homes or whatever it is. Okay, so some of the common chemical sedimentary rocks are limestone, chert, and rock salt. Okay, here's chert, this is rock salt, this is gypsum, and this is travertine. Okay, limestone is the most abundant chemical sedimentary rock, and it's mainly composed of the mineral calcite. I don't know if you remember from the minerals lecture, but calcite reacts with hydrochloric acid. So a good way to find out whether or not you're dealing with limestone is to use hydrochloric acid on these, and you'll see them effervesce. They can form from inorganic means or from biochemical origins. And the reason why they're important is because they have economic value. We can use it, grind it up to make cement. Okay, biochemical limestone originates from the shells of tiny marine organisms, or they can be macroscopic, larger organisms. Large part of marine limestone formed from coral reefs. Corals secrete calcium carbonate and create their homes, and they kind of built their apartment complexes one on top of the other, and they just expand and grow their communities. One incredible example of this is the Great Barrier Reef in Australia, and that's the largest coral reef on Earth. You can see it from space. It's incredible. Coquina is another biochemical sedimentary rock, and that's composed of fragments of shell material, just all kind of glued together, essentially, becoming a sedimentary rock. It's kind of like there are outcrops of coquina in St. Augustine. I don't know if you've been to the fort at St. Augustine, but the fort is built on that coquina. And just imagine, like, maybe you've been on Sanibel Beach or even to Lido Key in Sarasota. In those areas in Florida, there are a lot of shell fragments on the beach. So just imagine that material becoming a sedimentary rock. And then there's chalk, and chalk is composed of the hard parts of microscopic marine organisms. Okay, and perhaps you've seen that in classrooms where teachers use a blackboard and they kind of use chalk to kind of smear all over the place. But here it is. This is coquina. Okay, so this is what I was talking about, a bunch of shell fragments all kind of glued together. And this is Sanibel Beach. So yeah, try walking on this without any sandals. Ouch. Here's the Great Barrier Reef. It spans about 2,600 kilometers. It's incredible. Super long, and it's just thousands of different little coral communities, patch reefs, just kind of thriving in that warm tropical waters. So much of this material or limestone can be created that eventually, you know, with plate tectonics, if Australia ever runs into another continent or island arc or something, this limestone can be uplifted. And this has happened. In Texas, the Guadalupe Mountains here, that is a Permian-aged limestone reef that's exposed there. So here, now it's eroding away and going through its mass wasting processes. But this is an ancient reef that once was in tropical waters in Earth's past. All right, and then these are the White Cliffs of Dover. Okay, beautiful area where you have a huge outcrop of chalk. All of this is chalk. You could go over there and chisel out a tiny piece or a big chunk of chalk and just start writing on a blackboard. And what it's composed of is just billions and billions of these microscopic organisms. These are coccoliths. They're really tiny. This image is taken with a scanning electron microscope. They're not actually this color. This is just false color that's given to them, but they're really small. And so when they die, their shells, their remains, their bones essentially, drift down to the bottom of the ocean floor. That becomes sediment and eventually becomes a sedimentary rock, and that's chalk. Okay, so this is a bit weird if you think about it, right? You could be in class, physics professor is teaching you about acceleration, velocity, integrals, and they're smearing the dead remains of marine microscopic organisms to explain complex theories to you. Then there's inorganic limestone, and this forms when there are chemical changes in solutions, and calcium carbonate can precipitate directly out of the water. Okay, travertine is an example of this. This forms in caves. This is when the water that infiltrates and trickles down through the voids underground in a cave loses carbon dioxide, and then it'll crystallize calcite. Another example of this is oolitic limestone. There are outcrops of oolitic limestone in Miami, and these are really small spherical grains called ooids. And ooids are tiny little seeds that roll around in shallow marine water. And so what happens here is calcium carbonate is a bit strange. It actually precipitates out of solutions when water temperature rises. This is why, like, when you take a shower, I don't know if you ever noticed this, next time you jump in the shower, look at your shower head. If you take hot showers, especially here in Florida where we have hard water or a lot of calcium in the water, you'll see this white material kind of precipitate on your shower head. It's nothing gross or anything. You might be like, oh my God, it's grime. No, it's just calcium carbonate. That is precipitating directly out of your shower water onto your shower head. Okay, and in some environments where there's really warm marine water kind of crashing onto a beach, that can actually precipitate out these tiny seeds called ooids. Okay, so here's travertine. This is it slowly forming in a cave, drip by drip. And then these are those ooids. Okay, and this is oolitic limestone. And this is something we do have here in Florida. Okay, other chemical sedimentary rocks are dolostone. It's very similar to limestone, but instead of calcium, it contains magnesium. The exact origin of Dolostone is unclear. What scientists think occurs is that limestone or dolostone is created when magnesium-rich waters are circulating within a limestone, and it basically exchanges the calcium with magnesium. And then there's chert. Chert is composed of microcrystalline quartz, and this happens when you have dissolved silica precipitating out into sometimes into organic material or at the bottom of the ocean. This can also be the shells of marine organisms can form microcrystalline quartz. So here are some varieties of it. Here's petrified wood as one of those examples. Here's jasper and flint. This is all made up of really small microcrystalline quartz. All right, and then there are evaporites. These form, as the name suggests, when water evaporates away. Okay, so in restricted seaways, meaning in areas where there isn't much influx of seawater, maybe a narrow sea or a flat-lying area where there's flooded seawater coming in and there's very little precipitation and a lot of evaporation, those waters can be oversaturated and you get deposition of salts. Rock salt is one of them. That's pictured right here. Okay, and then there's rock gypsum, and that's right there. And so a lot of evaporites will form on salt flats. Okay, that's when this dissolved material precipitates as kind of a white crust on the ground. You can also find a lot of salt flats in Death Valley, California. This is a picture directly from the Morton website. These are the salt flats, and they're collecting salt. Makes our food taste delicious, doesn't it? One environment like this is the Bonneville Salt Flats in Utah. Okay, this area is almost 30,000 square kilometers with salt that are about 2 meters thick, hard white salt. Okay, this is where they do a lot of the land speed records. Okay, the last type of sedimentary rock is coal, and it's kind of in its league of its own by itself. Coal's different from all the other sedimentary rocks. They form from the carbon-rich remains of organisms. So a lot of times in coal, you can see plant structures or leaves or bark and wood. That's all identifiable in coal. You can see it pictured here. Okay, and it forms in 4 stages. Here they are. You have they form in swamp environments. Okay, and these are areas where when you have a lot of organic material that dies and may fall in water, and in swamp water, especially if there's a lot of organic matter piling into it and it's kind of stagnant water, it might be low in oxygen, and so that prevents the decay of a lot of plant matter, and you get an accumulation of organic matter that will create a soil called peat. And we actually have this in Florida. The Everglades would be kind of like a modern analog to how coal would form. Okay, then over time, as that peat soil has accumulated and in really thick amounts, okay, if it's then later compacted, it'll become lignite. Okay, and this is coal, but this is the lowest quality coal. Over more time, if there's more compaction, then you get bituminous coal, and then the formation of anthracite. And anthracite gives you the most energy, and this is environments that where there's actually been perhaps even mountain building or crustal deformation, and then you'll create anthracite. Okay, so how do you turn sediments into a sedimentary rock? Well, that is through diagenesis and lithification. A lot of changes can occur to the sediment after it's deposited. It's kind of weathered, transported, then deposited. Those processes are called diagenetic processes. Those are chemical, physical, and biological changes that occur after they're deposited. Okay, this occurs in the upper few kilometers of the crust, and some examples of this are recrystallization. Some minerals aren't stable in their kind of current form, so when they're thrust into a new environment, they'll recrystallize into something that is stable. And so another example would be formation of coal. That's a diagenetic process. Okay, so afterwards, the way you go from transported and buried sediment to a sedimentary rock is through lithification. And that's where you have unconsolidated sediments become a sedimentary rock. And that occurs in 2 steps. The first is compaction. So as sediments are buried, the weight of the overlying sediments as they pile and pile on top of each other compresses the deeper sediments, and it kind of squeezes out all the water from it. And then the next step is cementation, and that involves crystallization of minerals in between these sediment grains. So here's a picture showing that. Here's compaction. These are loosely buried sediments together, but over time, as more and more sediments add a lot of weight to it and pressure, they squeeze a lot of the water out, okay, and they compact this area. And then groundwater kind of moves through this area, okay, moves through the pore spaces, and then either silica or calcite will cement these grains together, and then voila, you have a sedimentary rock. So sedimentary rocks are classified according to the type of sedimentary rock and the texture they exhibit. Okay, so there are 2 major groups. There are detrital sedimentary rocks, which we've talked about, and then there's chemical and organic. Detrital sedimentary rocks have clastic texture, meaning that they have clasts in them or pieces or fragments of other rocks in them. Okay, chemical or organic sedimentary rocks have non-clastic texture or more crystalline texture. Okay, so that means the minerals form interlocking crystals. Okay, so this is how you classify sedimentary rocks. On one side, you have detrital sedimentary rocks. And remember, these are classified based on particle size, from the largest particles in conglomerates and breccias down through sandstone, siltstone, and the smallest particles, shale, over here. Okay, and that's indicative of different environments. So those are your detrital sedimentary rocks. On the other side, we have chemical and organic sedimentary rocks, and this is these are differentiated by composition. If you have a chemical or organic sedimentary rock that's made of calcite, then it could be a biochemical biochemical limestone. So that could be coquina, fossiliferous limestone, or chalk. And if it's formed inorganically, then we either have travertine or crystalline limestone. Then if it's quartz, these are the different varieties of chert or microcrystalline quartz. Gypsum, you have rock gypsum, or if it's an evaporite, rock salt. And then finally you have coal, and that's made up of altered plant fragments. So one of the most important aspects of sedimentary rocks is that they're kind of like we can look at environments today and then connect those environments to what environments were like in the geologic past. And that's really important. So if we know how sedimentary rocks form today, that kind of gives us a key to understanding what the past was like. And so a depositional environment or a sedimentary environment is a geographical setting where sediments are actively being accumulated. Okay. And there's 3 broad categories to these sedimentary environments. There are continental environments, there are marine environments, and there are transitional environments. Continental environments are sedimentary environments that are mostly dominated by rivers. So rivers run on the landscape, and they kind of carve their way through the landscape, and they erode areas, and they deposit a lot of sediments in different areas. So there's a lot of erosion and deposition. Then on another type of continental environment are glaciers. Glaciers are slower moving rivers, or ice rivers. They're really heavy, and they kind of scour their way through the landscape, and they leave behind U-shaped valleys, a lot of different features, but they create a lot of sediment along the way and deposit a lot of sediment at the end and on the sides of glaciers. And then there's the wind. The wind will will pick up very fine sediment. Okay, so that'll create kind of dune type environments or desert environments or loess deposits. And so those are very fine sediments, which means they're very well sorted. Marine environments include the shallow marine up to about 200 meters, and that's an environment that borders all the world's continents. They receive a huge quantity of terrestrial sediments. In addition to that, those areas where there are warm seas, you can have a lot of carbonate-rich muds and debris from coral reefs forming, or just, like the Great Barrier Reef. That's a huge marine environment. This also includes deep marine environments, and this is essentially going out towards the middle of the ocean from continental shelves. And here, what you typically see are very fine sediments, clay and silt-sized sediments that accumulate on the ocean floor. This is where shales will form. There are these underwater avalanches called turbidity currents, which are like submarine landslides, and they bring larger sediment to the deep ocean floor. But that's kind of an exception. Most of it is really small, fine particles that take 50 years to settle through the entire water column in the deep ocean. And then there are transitional environments. This is the last type of environment. Transitional environments are areas that are a transition zone between marine and continental environments. So think of the state of Florida and all the different environments that we have: beaches, tidal flats, spits, bars, barrier islands, lagoons, and deltas. So they're called transitional because the ocean rises and falls throughout geologic time, and sometimes these areas are under the ocean, sometimes they're exposed as sea level falls during colder times. Okay, so they're all here. This is where they're all represented. Okay, so we have stream environments, swamps where we get coal. This is glacial deposits here, or a dry area. We have a lot of sediment dumping out into a desert floor. Salt flats, here we have evaporites, sandstone forming in dunes, inorganic limestone in caves. We have rounded pebbles or conglomerate in a beach type environment. Here's sandstone forming in a beach. Here's a mud flat where we could have shale forming or siltstone. Here are those turbidity currents that come off of these canyons. This is all underwater here. Here's the continental shelf. Here's the slope, and then these canyons kind of cut right to the deep ocean. And so you have huge deposits over here. Okay, and then you also have deep ocean, deep marine deposits here. Then you have coral reefs, and then here landslides where you can have breccias form. So these are all representative of different sedimentary environments, right? And in sedimentary rocks, we often find sedimentary structures, and they provide additional information that we can use to interpret what went on in the past. Okay. So the most common feature in sedimentary rocks are called beds, okay, or bedding planes. So as sediment is deposited, it's kind of deposited layer by layer, with the oldest layers at the bottom, the youngest layers at the top. And then so you can see differences in sediment throughout geologic time. Perhaps even maybe there's a limestone and then a sandstone, and so that represents a changing environment through geologic time, and you can see that through the bedding planes. In some cases, we can see cross-bedding. Cross-bedding occurs when you have layers of sedimentary rocks that are inclined one way and then inclined another way, deposited on top of each other, and that's really characteristic of sand dunes. Deltas, for example, with shifting distributaries and rivers. Let's take a look at that. This is an example of bedding. So here's an outcrop of sedimentary rocks, okay, and these would be the bedding layers. Okay, and so they kind of just represent different time periods in Earth's history, with the oldest being down here, youngest up here. And then here are crossbeds. This is the Navajo sandstone from Zion National Park. Okay, and then so when we see a sandstone with specific structures like this, it's indicative of perhaps shifting sand dunes back and forth. And so that tells us that this environment was a lot like the Saharan desert in the past. And then there are another type of sedimentary structure called graded beds. This is a unique situation where sediments gradually change from like larger sediment sizes to smaller sediment sizes, okay? And this is associated with those turbidity currents I talked about. So this is this underwater kind of avalanche or deposit that occurs along these submarine canyons. See, this is San Francisco. Okay, here's a submarine canyon. And occasionally there'll be submarine landslides where this material just barfs and just deposits out onto the deep ocean floor. And what will happen is the heaviest material deposits out first, and then you get lighter material upwards. So you have large sediments depositing first, smaller ones just above that because their settling velocities are slower. And we call this graded bedding because from here upwards, the size of the particles are getting smaller. Then there are other sedimentary structures like ripple marks. That's pictured here. You see this out west a lot. Some people use this as tile, like on their patios or in their backyard. And this is really cool. I don't know if you've ever been out on a beach during low tide when the ebb current's kind of going out. You can see kind of ripple marks in the sand. That can be preserved in sedimentary rocks. Then there are mud cracks, which is pictured here. These are cracks that this indicates that this environment was wet and then went through a complete dry out, and it forms these kind of rectangular shapes of drying and caking of this essential this material, and that can be preserved in a sedimentary rock. Okay, so an environment that had alternately wet and dry spells. Okay, and then of course, most importantly, sedimentary rocks often contain fossils. Okay, those are the remains of prehistoric life. This is how we know what has existed in the Earth's past through this direct evidence of organisms like trilobites. Look at these guys. These guys existed 540 million years ago in our oceans, on the ocean kind of shallow bottoms, like moving around, crawling around in sediment. But that's incredible. And so, you know, any type of evidence of life that existed in Earth's past could be found in sedimentary rocks, and that's why they're so important.